Okay, so what we want to look at now is a basis for a vector space, right? Right, so I have some given vector space, big V here, and what a basis for a vector space would be, it would be some finite sequence, some sequence of vectors. In our case, the sequence is usually finite, right? Such that those vectors are going to be linearly independent and that they're going to span the vector space, right? Okay, so to give you an idea of what a basis is, let's recall this question that we did previously in the last lecture. Right, so I have a vector space which is R3. R3 is three-dimensional space, and I looked at a specific subspace of R3, which is this plane y is equal to x, right? Now you want to recall that what a subspace is. A subspace is a subset that is itself a vector space, right? Okay, so I'll just use this example over here. I can just regard the W over here as a vector space in itself, right? So W is a vector space that's contained inside a larger vector space, but we're focusing on a W, right? Okay, so for this W, which is this plane over here, right? Well, what would be a basis for this plane, right? I'm saying that a basis for this plane would be these two vectors, this vector 1, 1, 0, that is on my xy plane, and this vector 0, 0, 1 would be, these two together would form a basis for my vector space, which is W over here, right? Okay, so given a vector space, a basis is some finite set of vectors that is going to have two properties, right? That it's going to be the vectors, such as these two vectors over here, they're going to be linearly independent, right? And they're going to span the vector space, right? So these two here, right? These two vectors, they're linearly independent. You can check formally that these are linearly independent. If you have two vectors, two vectors are going to be linearly independent if one is not a multiple of the next one, right? And clearly this vector is not a multiple of this one, right? These two vectors are linearly independent, and we saw last time that these two vectors, if you take linear combinations of these, that will span the entire W over here, right? So these two vectors, the 1, 1, 0, and then the 0, 0, 1, right? These are going to form a basis for this vector space W here, right? Okay, so this is my definition, right? So the definition is saying that if I have a vector space, right, what a basis is going to be is a basis is going to be some finite sequence of vectors, right? So by sequence, I care about the order, right? And later on, you'll see that the order, the basis vectors are important, right? Okay, so this, for example, I'll call this one V1 over here, I'll call this V2. And here I have two basis vectors for my vector space, which is W, right? And a basis is a sequence of vectors in V that are linearly independent, right? So these two are linearly independent and that they span the vector space, right? And these two here span the vector space W. Right, okay, so as our next example of a basis, right, let's consider this over here. So I have this, if you want, this is your x-axis over here, and this is your y-axis over here. And this is supposed to represent the xy plane, right? And this vector over here, this is vector 1, 0, right? And this is the vector 0, 1, right? Okay, so this vector 1, 0 together with this vector 0, 1, right? I'm saying that these two vectors over here, they're going to form a basis for your plane R2, right? Okay, so in order for it to be a basis, you need to check that they're linearly independent, right? And we can check, right? And I'll do an example in a while where I'll show that these two, well, I'll actually show this in a second, that these two over here, these are linearly independent, right? And these two, what they will do is they will span the plane, right? So any vector in R2, right, you'd be able to express as a linear combination of these two, right? So as an example, let's say I have this vector over here, which is the vector 2, 4, right? Okay, so this vector over here, this is some vector in two-dimensional space, and I can actually express this vector as a linear combination of these two, right? And that's essentially, that's giving you an idea what span means, right? And we talked about the definition of span. If I have any vector in the plane over here, I can express any vector in the plane as a linear combination of these two, right? Okay, so for example, you see that this vector, the vector OP, right, I can express as a linear combination of 2 times E1, right, plus 4 times E2, right? Okay, so E1 is unit vector in the x direction, E2 is unit vector in the j direction. Okay, and this vector over here I can express as a linear combination of these two, right? And you see it over here, right? This vector OP is a linear combination, so it's 2 times E1 plus 4 times E2. Okay. All right, so any vector in R2 can be expressed as a linear combination of the two vectors E1 and E2, right? And E1 and E2, I'm saying that these are linearly independent, right? So what that means is that your vectors E1 and E2, right? These vectors over here, these would form a basis for two-dimensional space R2. Right, so we're still looking at R2, the vector space, right? And said that the E1 and the E2, right? The 1, 0 over here and the 0, 1 over here. And this would be one basis, a basis for R2, right? Now, this is not the only basis, right? Your definition of basis is that any basis, the vectors would need to be linearly independent and they will need to span R2, right? Okay, so another basis has to be linearly independent and it will have to span, right? So I'm saying, well, as an example, right, this over here, these vectors u and v, where u is 1, 1 and v is minus 2, 2, right? These two over here, that would also form a basis for R2, right? So these two vectors over here, right? These two are linearly independent and they actually span R2, right? And to give you an example of why they span, right? Consider, say, this vector here, right? Okay, so this is some vector in R2 and I'm saying that any vector that I choose, like such as in R2 over here, right? I can actually express as a linear combination of these two basis vectors, the red one and the green one over here, right? To see that you see over here, right? Okay, so this somewhat arbitrary black vector over here, I can express as a linear combination of the u vector, right? So 3 times u, and then a half v, right? So 3u plus a half v, right, gives me my vector OP over here, right? Okay, so you see in 3 times the vector u plus a half times the vector v, right, gives me this vector 2, 4, right? Okay, and you can in fact, if you move this p around, right, you see in that any vector, right, any vector in the plane R2, right, you can actually express as a linear combination of the u and the v over here, right? So definitely the vectors u and v, right? The vectors u and v, they span, right? And it's not hard to check to see that the u and v are also linearly independent. Let's do this example here, right? And we'll go through formally the checks to see that this basis, this 2, 4 over here and this 1, 1 is in fact a basis for a vector space R2, right? Okay, so I drew the vectors 2, 4 and 1, 1 over here, right? But and while the diagram is nice and so, right, and you can see, for example, that Okay, I can express a vector, any vector in R2 as a linear combination of the vectors u and v, right? The vectors, in fact, these vectors here, right? The u and the v here, right? Okay, they actually, these are linearly independent because they're not multiples of each other, right? Unfortunately, they more or less sort of point in the same kind of general direction, right? So while they will work as basis vectors, right, the linear combinations that you're going to get out of them are going to look a little strange, right? But for the purposes of actually formally showing that these two are gonna, so the red one and this red one and this green one, right? So for the purposes of showing that red and green are actually uh, a basis of R2, right? They'd be good enough, right? Okay, so we want to show that these two vectors, your 2, 4, and the 1, 1, they're gonna form a basis for a vector space R2, right? Okay, so if it's going to be a basis, it needs to satisfy two conditions. It needs to be linearly independent, and it needs to span the vector space, right? Okay, so how do we check uh, that these two vectors, that they span the vector space R2, right? Well, what does span mean, right? Span means that if I have any vector, right, in R2, right, so, and I represent any vector over here as AB, right? So this AB over here represents an arbitrary choice of a vector in R2, right? So for example, this black one over here, you could think of as some arbitrary choice of a vector in R2, right? And matter of fact, you could just move it around, right? But the point is over here, you choose, you want to say that any vector in R2, you want to be able to express it as a linear combination of these two vectors over here, right? And how you do that is you make this any vector over here arbitrary. And how you make it arbitrary is you use a variable here for your first component, small a, and you use a variable here for your second component, which is small b, right? Right. Okay, so now what you want is you want to say that, all right, so I have this arbitrary vector AB, right? Can I actually express it as a linear combination of your vector, this first vector here, 2, 4, and this second vector here, 1, 1, right? Okay, so what does it mean that I can express this AB as a linear combination of the 2, 4 and 1, 1? It means that if I have a scalar times 2, 4 and a scalar times 1, 1, I'll get this vector AB, right? Okay, so I should be able, if I can write AB as a linear combination of the 2, 4, and 1, 1, right? It means that I need to be able to find the scalars C1 and C2 such that C1 times 2, 4 plus C2 times 1, 1 would give me the vector AB, right? Okay, so, well, how do I find the C1 and the C2, right? Well, how you find the C1 and C2, you just want to realize that this setup over here is just a vector equation, right? And for the time being, you really, while I'm saying the AB could be arbitrary, right? Once you get to the point of this vector equation, right? The A is actually fixed and the B is fixed now, right? And what you're trying to do is you're trying to solve for the C1 and C2 in terms of the A and the B, right? Okay, so, well, what do you do here now, right? So I want to get C1 and C2 in terms of A and B, right? And how I do that is I just multiply out, right? So I'm going to get C1 in the first component over here. I'd have 2C1 plus C2 is equal to A, right? And that gives me this first equation. Okay, and then I'm going to have 4C1 plus C2 is going to give me B over here, right? So I get my second equation, which is 4C1 plus C2 is equal to B, right? So I have these two equations here, right? And what I want to do is I want to be able to solve them, right? I want to solve, so I want to get the C1 and C2 values such that when I put it in over here, I'm going to get the A and the B, right? And that's equivalent to finding the C1 and C2 values that satisfy this 2 by 2 system of equations here, right? Okay, and what you want to do, so now what you want to do is you want to solve this 2 by 2 system of equations. And how you do that is this is a system of equations that we saw from before, right? Okay, so for this system, what you do is you form your augmented matrix, which is the 2, 4, and 1, 1 over here in the second column. And then the A and B would be on this right-hand side over here, right? Okay, and how you go about solving the system is once you form your augmented matrix, you apply Gauss-Jordan, right? And when you apply Gauss-Jordan to this, right, you're going to get an RREF, which is this RREF over here, right? And notice the right hand side over here, right, is in terms of A and B, right? Because when you add in and subtracting your rows, you're going to get these components here in terms of A and B, right? Anyway, so what you have is you're going to have that you have this RREF, and remember an RREF is corresponding to a system, right? So from this RREF, which is an augmented matrix, you form the associated system, right? And with this associated system, what you're doing is you're seeing that, okay, so this first row is saying that C1 times 1, which is C1, plus 0 times C2, which is 0, right? So I'm going to get C1 over here is equal to B minus A on 2. So I get this equation. And then likewise from the second row, I get this equation, right? Okay, so what that tells me is that C1 is equal to B minus A on 2, and C2 is equal to 2A minus B, right? And if I put the B minus A on 2 in over here, and I put the 2A minus B in for C2, right? You realize that C1 is equal to B minus A on 2, and C2 is equal to 2A minus B. When you expand out that left-hand side, you're going to end up with A and B over here, right? Okay, so what that means is that for any vector AB, such as this black vector over here, I'd always be able to find scalars C1 and C2 such that the vector that I chose could be written as a linear combination of the 2, 4 and the 1, 1, right? So the C1 times the 2, 4, right? Okay, so given the AB, I'll find a C1 and a C2, right? That depend on A and B. What I put when I put it in over here and I put it in over here, right? This will work out to be AB, right? So that says that the AB is a linear combination of the 2, 4 and the 1, 1. Remember, this AB is arbitrary, right? So what this means is that any vector in R2 I can express as a linear combination of the 2, 4 and the 1, 1, and that actually means that these two vectors 2, 4 and 1, 1 they span R2, right? Because the definition of span in R2 means that any vector in R2 I can express as a linear combination of these two vectors. Okay, so that sorts out the span, right? And now what we want to do is, okay, so to check to see if something is a basis, we need to check to see that it spans the vector space, right? The next thing now that we want is we want to see that these two vectors over here are linearly independent, right? Okay, so how do you check for linear independence, right? How you check for linear independence is you form this vector equation over here, right? Okay, so C1 times your first vector 2, 4, C2 times your second vector 1, 1, right? And what you do is you put the 0 vector on this side, right? So recall your definition of linear independence. If I want to show that the vectors 2, 4 and 1, 1 are linearly independent, what I'm going to do is I'm going to set up this vector equation where my right hand side is equal to 0. So right hand side is equal to 0. And I'm going to have C1 times the first vector and C2 times the second vector, which is what I have over here. Set it equal to 0. What you do is you look at this vector equation over here, right? And you solve, right? And if when you solve, you get a unique solution that the C1 is 0 and the C2 is 0. In other words, the C1 must be 0 and the C2 must be 0. So your vector equation forces the C's to be 0, right? Then that means that these vectors 2, 4 and 1, 1 are linearly independent, right? Okay, so what we need to do is we need to solve this vector equation, right? But you want to realize that this vector equation here, right, is really exactly in the form of this vector equation 2.6, right? This vector equation here, right? Okay, the only probably small difference is that here what I have is AB, right? And here I have 0, 0, right? Remember, this A, B is arbitrary here, right? So what it means is that I can use anything I want for A over here and anything I want for B over here. And in particular, I could use A is equal to 0 over here and B is equal to 0 over here, right? So all this working over here, where I get C1 and C2 in terms of A and B, right? I could essentially just use it here, right? Okay, so this is the A over here and this is the B over here. So from above, I have that the C1 is equal to B minus A on 2, right? And the C2 is equal to 2A minus B, right? And in this case, the A is equal to 0 and the B is equal to 0. So I end up with the C1 is equal to 0 and the C2 is equal to 0, right? And that's the unique solution, right? There are no other solutions, okay? So what that tells you is that if I have this vector equation here, right, where 2, 4 is the first vector and 1, 1 is the second vector, and I form my standard vector equation to test for linear independence, right? This vector equation implies that the scalars is 0. So the 2, 4 and the 1, 1 are linearly independent, right? Okay, so the linearly independent, so what do we have now? We have, first of all, we show that the 2, 4, 1, 1, that these two vectors, they span R2. And over here, we just showed that they're linearly independent. So by definition, it's going to form a basis for my vector space R2, right? So basis is a set of vectors, a sequence of vectors that are both linearly independent and that they span the vector space. And we showed that in this case here, right? Okay, so I just showed that these vectors 2, 4, 1, 1, and I showed formally that these two vectors, they're linearly independent. Well, first I showed that they span R2, and then I showed that they're linearly independent, right? Okay, so the span R2 and they're linearly independent means that they're a basis for R2, right? So these are the two vectors over here. This is the 2, 4. Okay, so this is the 2, 4 here. The 2, 4 is the red arrow here, red vector, and then the 1, 1 is your green vector over here, right? Okay, so these would form a basis for R2, right? And now I'm going to look at a second example. So I'm going to look at a second possible basis, right? And this basis now is 1, 0, 0, 1, right? So I'm going to say that, I'm saying now that basis 1, 0 and 0, 1 over here, these are going to form a basis for R2, right? Okay, so let me draw these here, right? Okay, so that's what they look like, right? So notice the first vector is lying along the x-axis and the second vector is lying along the y-axis, right? I'm sure you all know that these are standard basis vectors. So this is of length 1, and people sometimes call this I, right? And they call this one over here j, right? So this is vector I, vector j. But the notation that we will use in this class is if we're looking at for example R2, right? Your first basis vector that is lying along one of these axes is E1, and then the second one is E2 over here, right? Okay, so what I want to do is I want to show that the E1 and E2 now this is also a basis for R2, right? So while these the red and green ones, these two over here were basis, this second set consisting of the 1, 0 and the 0, 1 is also a basis, right? So these two over here, these are a basis, right? And likewise these two over here are basis, right? And I showed that these two are basis already. What I want to do now is I want to show that the standard basis vectors over here, these are going to form a basis, right? Right, okay, so how will I do that, right? Well, how I do it is really the same sort of working as what I had across here, right? So it's the same ideas, right? What I want to do is I want to show that these two vectors, that they span R2, right? And that they're linearly independent, right? Okay, so how do I show that these two vectors span R2, right? For to span R2, it means that any vector in R2, which I can write as AB, right, I can express as a linear combination of the 1, 0 and the 0, 1, right? So I need to be able to find the C1 and C2 in terms of A and B such that this is true, right? Okay, and how do I do that? Well, this is just a vector equation, right? So as a crosshair, what I did is I multiplied out, right? So you multiply out and you look at your first component here. I'd have C1 is equal to A, right? If I'm just looking, so C1 times 1 plus 0 times C2, which is just C1 on this left hand side, and I have a right hand side, which is A. So this gives me C1 is equal to A. And likewise, looking at the second component over here gives me C2 is equal to B, right? Okay, so what that means is if I have any A, B over here, I can write it as a linear combination of the 1, 0 and the 0, 1, right? And you should realize, well, I could just use A over here and I just use B over here. And that's what solving gives me here, right? Okay, so any vector AB I can write as a linear combination of the 1, 0 and the 0, 1, which means that these two vectors, they span R2, right? Okay, and then once you show the span, right, what you could also do is you can now you need to show the linear independence, right? Okay, so how do you show the linear independence? What you do is you consider this vector equation, right? So you have these two vectors here. You want to show that they're linearly independent. So it's C1 times this vector 1, 0, and then C2 times the vector 0, 1 here, right? And set that equal to the 0 vector, right? And what you do is you solve this, right? And you solve this and see if the C1 must be 0 and the C2 must be 0, right? Okay, but how do you solve this? You could expand it out over here, right? Or you could really just use the equation, the working that we had from above here, right? Notice this vector equation is the same as this vector equation over here. The only difference is that, well, here this is arbitrary A and B, and this is 0 here and 0 here, right? So in other words, the A is equal to 0 and the B is equal to 0, right? So when I solve this using this working, what I'll get is C1 is equal to A and A is equal to 0, so I'll get C1 is equal to 0. And then I use the B is equal to 0 to give me C2 is equal to 0, right? Alright, so what I get is C1 and the C2 must be 0, so this vector equation implies that the scalars must be equal to 0, so the vectors 1, 0 and 0, 1 have linearly independent, right? Okay, so vectors 1, 0 and 0, 1 are linearly independent and they span R2, and hence they are basis for R2. Okay, so we could consider a three-dimensional vector space now, right? So R3, right? Okay, so R3 is a three-dimensional vector space, right? And a basis for R3, right, would be vector 1, 0, 0, right, which is 1, 0, 0, which is along your x-axis over here, 0, 1, 0, which is along your y-axis here, and 0, 0, 1, which is along your z-axis here, right? Okay, so these three vectors over here would form a basis for a three-dimensional space, right? Okay, and in the notation that we use in this class, right, your first one is E1, second vector is E2, and the third one is E3, right? Well, these correspond what you'd know from your vector geometry and so on, right? You could also call this I over here, J over here, and K over here, right? Okay, so how do you show that this is a basis? Well, the working is really very similar to what I have for R2, right? So what you do is you'd form your vector equation, right? Where you have arbitrary A, B, and C now on the side, right? And then you'd show that these vectors that they span, and then you'd form your standard vector equation to check for linear independence over here, and you'd show that the C's must all be equal to 0. So you'd prove the linear independence. So you prove the spans and the linear independence, and that would show that this is a basis for R3, right? So this E3 over here, capital E3, is a basis for R3, right? And as I said, the working is essentially the same sort of working as what we did for the standard basis for R2, right? The only difference now is now you have three components, right? Okay, so let's recall that this P2 over here, what this is this is the vector space of polynomials of degree at most 2, right? And we saw the definition, the general definition, in the case of Pn, right? So what this means, this is polynomials of degree at most n over here, right? So I'm saying over here that the n is equal to 2, so polynomials of degree at most 2, right? Okay, so this here is a vector space where the vector addition is the usual addition of polynomials, and the scalar multiplication is usual uh, multiplication of a polynomial by a scalar, right? Okay, so this here is a vector space, and I want to show that this 1, x, and x squared, right? This would be a basis for your vector space P2 here, right? Okay, so how would you show that this 1x and x squared, it's a basis, right? Well, what you need to do is you need to show the same two things that have been shown for the other cases, right? I need to show that it is linearly independent, right? Okay, so that these three are linearly independent and that they span the vector space, right? Okay, so we saw in the previous cases that it's easier, or probably best to show that it spans first, because the working that you use for spans, right, you can just later on use for showing the linear independence, right? So you save yourself some working, right? Okay, so these three overhead, 1x and x squared, I'm saying it's a basis from polynomials of degree at most 2, right? So how will I show spans, right? Well, spans means that if I have an arbitrary element of P2, an arbitrary vector in P2, and the vector in P2 is a polynomial of degree at most 2. Well, the arbitrary polynomial of degree at most 2 I can write this way, a plus bx plus cx squared, right? Okay, and what I want to do is I want to show that this here can be written as a linear combination of the 1, the x, and the x squared, right? So in other words, some constant times 1, next constant times x, and the next constant times x squared, right? This linear combination, right, would give me the a plus bx plus cx squared for any a, b, and c that I have here, right? Okay, so at this point in time, what you do is you say, well, all right, the a, the b, and the c, they're more or less fixed, right? And what you do is you try to figure out, well, can I get a c1 and a c2 and a c3? That would give me a, b, and c over here, right? And what you want to do is, well, these are polynomials, and this is a polynomial on this left-hand side. It's a polynomial on this right-hand side. And the only way for these polynomials to be equal to each other is if the powers, the coefficient of the corresponding powers are the same, right? So for example, the coefficient of the x squared over here is c, and that needs to be equal to the c3 over here, right? Okay, so I get my third equation, c3 is equal to c, right? And likewise, looking at the power of x to the 1, right, I get c2 over here is equal to b over here, right? And likewise, the power of x to the 0, or just a constant term, right, is c1 over here and a over here, so this gives me c1 is equal to a, right? So what that says is, if I have any polynomial over here, right, from my vector space P2, I can always just use C1 is equal to A, C2 is equal to B, and C3 is equal to C to give me this polynomial. In other words, I can express any polynomial in P2 as a linear combination of these, right? Okay, right, so these polynomial, these 1x and x squared, they generate P2, right? They span P2. Right. Okay, and next what you want to do is you want to check for linear independence, right? Okay, so how do you check for linear independence, right? Again, you're using a definition of linear independence. Okay, so your definition of linear independence is you form your vector equation, set it equal where you have 0 on this right hand side, and what you do is you solve, right? And if when you solve you get the unique solution that the c's all are 0, right, then that means that the vectors that you have are linearly independent, right? So in this case, these are the vectors 1, x, and x squared, right? Okay. Right, so the 1x and x squared, you set up your vector equation, you have 0 on your right hand side, and the 0 vector in this case is the 0 polynomial, and the 0 polynomial is just 0, right? Or you could also think of your 0 polynomial in this case, because we're in P2, is when we have 0 for the constant term, 0 for the term in x, and 0 for the term in x squared, right? Okay, so I have my vector equation over here, and because from using equality of polynomials, the only way this equality would hold is if the C1 is 0, the C2 is 0, and the C3 is 0, right? So the C's must all be equal to 0. So that tells me that these 1x and x squared, that they're linearly independent, right? Okay. Well, a next way you could see this is if you're just doing addition, linear combinations over here, right? There's no linear combination of the 1 and x that would ever give you the x squared, right? If you have a scalar times 1 and a scalar times x, whatever linear combination you have involving the 1 and the x will never generate x squared for you, right? So that's probably a next way to conceptualize linear independence here, right? Anyway, so the 1x and x squared are linearly independent, right? So these three vectors, right? They span P2, right? And they're linearly independent, and therefore it's going to be a basis for P2. Alright, okay, so let's look at theorem 2.36, right? Okay, so I'm going to consider a vector space, and this is a vector space that is not just a trivial vector space, right? So this vector space this theorem is going to apply to vector spaces that have non-zero vectors in them, right? So not just your trivial vector space. Okay, so if I have a vector space and I look at, and so given your vector space and given some fixed basis of my vector space, right? So this, for example, this is R2. This is R2 over here, and this U and V here. This is gonna form a basis for R2, right? And we showed how to prove that the U and V two vectors like this would form a basis for a vector space, right? So the U and V over here, this red and green one, right? These are going to form a basis for R2, right? And what this theorem is saying is that if I have any vector in the vector space, such as this one here, right? Such as this black one, right? Then I can express this vector as a linear combination of the U and V, right? Okay, so I can express my vector, any vector in the vector space, so represented by this black vector here. I can express it as a linear combination of the U and the V, right? Okay, and so you see in here that this black vector is a linear combination of the U and the V, right? And the software over here is actually working it out for you, right? It's finding the code, it's finding the constants here, the C1 here and the C2 over here, right? Such that you get okay, so this black one over here, which is the right hand side, could be expressed as a linear combination of the red one. In other words, the red one times some scalar, and then the green one times some scalar over here, right? And when you add these two, you get this black one on the right hand side, right? Okay, so every vector of the vector space can be expressed as a linear combination of the basis vectors. And let me remind you that the basis vectors, these over here, right? These are the basis vectors, the U and the V. Right, but the point about this theorem is, and we actually already have an idea that this is true, right? Because if I have any vector, the fact that the U and the V are basis means that if they are basis, if the U and the V are basis, right, it means that they span the plane, right? And if they span the plane, any vector in R2 can be written as a linear combination of the U and the V, right, of the basis vectors, right? The point about this theorem is it's telling you something about these scalars over here, right? These scalars are unique, right? You can't find any other scalars that would satisfy this vector equation, right? So that is what theorem 2.36 is saying, right? if I have a basis to start off with, right, and I have some vector, any vector in my vector space, right, then I can write this vector as a linear combination of my basis vectors. I can write them as a linear combination of the basis vectors, and the scalars that form this linear combination, these scalars over here, it's unique. Okay. Okay, so your scalars over here are unique, right? And what we want to do is we want to keep track of these scalars over here, right? Okay, so for any vector, such as this black vector over here, I can express the black vector as a linear combination of the u and the v, right? And with a linear combination, you need scalars here and scalars here, right? And what the theorem is telling you is that these scalars are unique, right? And so for your basis u and v, you have associated scalars here, c1 and c2, right? That are corresponding to this black vector here, right? Okay, and these scalars here, right? This 1.13 and 2.15 in this example, right? These are in fact called coordinates of your black vector here, coordinates of this black vector with respect to the basis vectors u and v here, right? So these values, the c1 over here, the 113 and the 215, right? Those are example of coordinates, right? The coordinates with respect to some basis. Okay, so I said that this scalar 1.13 and the scalar 2.15, right? These are coordinates of this vector, your black vector over here, with respect to your basis vectors u and v, right? And the basis vectors are these over here, right? These are the vectors u and v, right? Okay, so let's see the definition of coordinates, right? Okay, so coordinates are with respect to basis, right? So I have a finite dimensional vector space, right? And we saw an example of okay, so most of the vector spaces that we will look at in this class are finite dimensional, right? In other words, if you're looking at a basis for your vector space, right, that basis is only going to have a finite number of elements, right? So for example, with R2 here, right, R2, this two-dimensional vector space has R2, which is the plane, right, has two basis vectors, right? Okay, so your basis contains only a finite number of vectors. In this case, the finite number is 2, right? In the case of, for example, R3, right? R3 three-dimensional space, the basis, this is a basis here, E1, E2, E3, right? Your standard basis vectors, right? So these three vectors here, these would form a basis for three-dimensional space, right? And you want to notice that this is finite dimensional, right? The number of vectors in your basis is 3 in this case, right? Okay, so both R2 and R3 are finite dimensional, right? We saw an example of something that is not finite dimensional. So, for example, if you consider polynomials, right? Polynomials not of any fixed degree, but any polynomial, a vector space of all polynomials, that in fact is not a finite dimensional vector space, and we did that in a previous lecture. Right. Anyway, so for this definition here, this definition for coordinates, right, hinges on the fact that the vector space that we're looking at is finite dimensional, right? Okay, so I have a finite dimensional vector space such as R2 over here, and I have a basis fit, right? So I have some basis fit like this U and V over here, right? Right, and what the coordinates are is that if given some vector, right, some other vector, right, I can express that vector as a linear combination of my basis vectors. Okay, so this black vector over here can express as a linear combination of the basis vectors. And then once I do that, the scalars out in front here, which correspond to the x1 and the x2 and so on, right? Those would be your coordinates, right? So in this case, the x1 is 1.13 and then the x2 is 2.15, right? Okay, so looking at this definition, if I have a finite dimensional vector space and I have the basis vectors for my finite dimensional vector space, so I have some fixed basis over here, right? If I take any vector in my vector space, right, I can express that vector as a linear combination of the basis vectors, right? And the scalars in front of the basis vectors in this linear combination, what you want to do is just you want to keep track of the scalars alone, right? And those scalars are called coordinates of this vector u over here with respect relative to your basis vectors over here b, right? And next definition is, okay, so this is, for example, if we look at x2 is your second coordinate of your vector u relative to the basis v, right? And more generally, xi is the ith coordinate of your vector u relative to the basis v, right? Okay, and you can, so given u written in terms of given u written as a linear combination of your basis vectors, right? What I said is you just want to keep track of the scalars in front over here, in front of the basis vectors. So in other words, the x1, x2, up to the xn. Those scalars, you keep track of those, and you could write them either in a row vector form or a column vector form, right? So you can write your coordinates either as a row vector or as a column vector. Alright, okay, so let's take a look at an example of finding coordinates relative to a given basis, right? Okay, so I have a vector space which is R2, and I have basis vectors 2, 4, and 1, 1, right? Okay, so this is my vector space R2, and I have vectors, so 2, 4, and 1, 1, right? And these two form a basis, and we showed this, right, that these two are going to form a basis for R2, right? So your red and green one here, they form a basis for R2, right? Okay, and what we want to do now is we want to get coordinates of this vector, which is, we want to get the coordinates of the vector 1, 2, right? So this column vector here, 1, 2, relative to the basis 2, 4, and 1, 1, right? Okay, so your vector 1, 2 is this vector over here, right? And you want to notice that your vector 1, 2 in fact lies along your first basis vector, right? Okay, it just happens in this case that this your given vector 1, 2 lies along your vector 2, 4, right? Matter of fact, it's half the length, it's half of the vector 2, 4. Okay, so what we want is we want the coordinates of 1, 2, right, relative to basis 2, 4, 1, 1, right? Okay, so what are the coordinates, right? The coordinates would be of your vector 1, 2 relative to your basis vectors 2, 4, and 1, 2 means that it's these scalars, the coordinates are the x1 and x2, right? Such that when you put in the x1 over here and the x2 over here, this works out to be 1, 2, right? So in other words, your coordinates, coordinates of these scalars that would solve this vector equation, right? So given this vector equation over here, coordinates are just going to be the solutions of this vector equation, right? And well, how do you get the solutions of this vector equation? Well, what you do is you just multiply out, right? So along for your first component, you're going to get 2x1 plus x2 is equal to 1. And likewise, considering your second component, this gives you 4x1 plus x2 is equal to 2, right? Okay, so I have this system of equations, and you can just solve this in your normal way. You form an augmented matrix, right? apply Gauss-Jordan to get an RREF, right? And you want to notice that this has a unique solution, right? You have no free variables over here, right? Your variables of your system are x1 and x2. Both of those, x1 is a pivot variable, x2 is a pivot variable. So you have no free variables, right? Your system is consistent, so you're going to have a unique solution over here, right? So you get that the x1 is a half, right? Okay, so read in what this RREF, right? What you could do is you form the associated system, and the first row of this RREF tells you that the x1 is a half. The second row tells you that the x2 is equal to 0, right? So you get x1 is a half, x2 is equal to 0, right? So your coordinates would be a half over here and 0 over here, right? In other words, this one isn't really, the 1 isn't forming part of your calculation. You're just going to get a half times this 2 4 would give you the 1 2, which is what you expect, right? Because this vector 1 2 is, well, it's a half of this vector 2 4, right? So you expect this x1 to be a half, and you expect the x2 to be equal to 0, right? And the software, it actually calculates it for you, right? You have your basis vectors 2 4 and 1 1, right? And it finds the coordinates for you, right? The coordinates are the 0.5 or the half, right? And so the x1 is 0.5 and the x2 is equal to 0. Okay. Alright, so going back to our vector space R2, right? We showed that the u and the v, right, which would be the red and the green one here, right? These vectors here, these would form a basis for R2, right? Notice you have two vectors in your basis for R2, right? Okay, and then we also saw, and we actually showed, right, that your standard basis vectors, the E1 and the E2 over here, these are also a basis for R2, right? Now, what you want to notice, there's also two vectors in this basis, right? There are not three vectors in this basis over here, there's just two, right? So if I have this basis here, right, I have two vectors in it. And if I have this basis here, right, I have two vectors in it, right? So my first basis, if you want, the red and the green one has two vectors in it. And the second basis, the E1 and E2, has two vectors in it, right? So, and I can, well, for R2, right, what's going to happen is if you have any basis for R2, any basis for R2 will have exactly two vectors in it, right? It won't have one vector, it won't have three vectors, right? It will always have exactly two vectors in it, right? Okay, and we saw an example of it, right? So the E1 and the E2 is a basis, and that's two vectors in that basis, and this also, the U and the V over red and the green, right? This is also a basis, and you have exactly two vectors in it, right? So any basis for R2 will have exactly two vectors in it, right? And that is the statement of this theorem here, right? If I have a finite dimensional vector space, all bases are going to have the same number of elements, right? So you could have different bases, right? Okay, so for example, the black one over here, that is one basis, and then the red and the green, that is a different basis, right? But the point is, with the different bases, right, if you have different bases, that's fine, right? But each basis will always have the same number of vectors, right? So in this case, for R2, this basis has two vectors in it, and your different basis, which is this one over here, also has two vectors in it, right? And that works for any finite dimensional vector space, right? The proof of this is a little technical, right? And we're not going to get into that, right? If you want, you could take a look at it, right? It's somewhat interesting. Right, okay, so now that if I have a vector space, right, and I have a basis fit, right, any basis that I have would always have the same number of elements, right? Okay, and that number for your a basis for a vector space is in fact called a dimension, right? Okay, so for example, if we're in R2, right, the number of vectors in this basis here, the number of vectors in this basis over here is 2, right? If I have a different basis, this one over here, the number of vectors in it is 2, right? Okay, so what we're interested in is that number 2, right? So if you have a vector space such as R2 and you consider any basis for it, right, and you count the number of vectors in it, right, that number is not going to change from one basis to the next, right? It's always going to be fixed, and that number we call the dimension of the vector space, right? Okay, so dimension of a vector space is of a finite dimensional vector space is simply the number of vectors in any of its bases, right? So if you have a finite dimensional vector space, you just find a basis, you count the number of vectors in it, right? And that's the dimension of the vector space, right? And it's denoted as dimension v, right, or dim v here, right? Okay, so when I say, for example, that I was saying previously that R2 is two-dimensional, right? And it's two-dimensional because, well, you have an x-axis and a y-axis, right? And you're in the plane, right? And the plane is say, basically flat, right? Two-dimensional. That's all well and good, right? But the precise meaning of dimension is that if it is a vector space and you find a basis for it, right? Okay, so R2 is a vector space. You can find a basis for it, and any basis that you find for it would always only have two vectors in it, right? And that 2 is called a dimension, right? Okay, so R2 is a two-dimensional vector space because any basis has two vectors in it. Alright, so let's look at the dimension of certain vector spaces, right? Okay, so we just saw that R2, right, is two-dimensional, right? Because any basis for R2 has exactly two vectors in it, right? So that's R2, right? And if we now consider, say, R3, right, which is R3, a basis for R3 would be your I, J, and K, right? 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? Okay, so these three over here, these three vectors would form a basis for R3. So what that means is that the dimension of R3 is 3, right? Okay, so R3 is a three-dimensional vector space. Okay, and more generally, so if we're looking at R3, right, your standard basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? Okay, and the standard basis vectors for R2 are 1, 0, and 0, 1, right? Okay, so notice there's a pattern in forming these standard basis vectors, right? Your first standard basis vector would have 1 in the first position, right? And then 0s elsewhere, right? Second one would have 1 in the second position and 0 elsewhere, right? So that's the case of R2, right? Your standard basis vector for R3, right? You have 1 in the first position and 0 in the other positions. For your second standard basis vector, you have 1 in the second position and 0 is everywhere else, right? And for your third basis vector, you have 1 in the third position, right? So for the first, so just your standard basis vectors are just going to have it's 1 somewhere and then 0 everywhere else, right? And where the 1 is depends on whether you're looking at the first vector, the second vector, or the third vector, right? So if it's the third vector, the 1 is going to be in the third position, right? Alright, so this is your standard basis for R3, right? And if you want to consider more generally, right? So for Rn, right? So n-dimensional vector space, right? What you want to do now is you want to consider that you now have n, your column vectors are now going to be of length n, right? Okay, and what you do is you use this sort of notation over here, right? With the these sort of dots here to indicate that you have a length of n over here, right? Okay, so E1 would have 1 in the first position, E2 would have 1 in the second position. And remember, now you have n of these, right? So you have n entries in your column vector, right? Okay, so it means that if you keep going like this, you're going to have 1 in the first position, 1 in the second position, and then you're going to come down to having 1 in the nth position, right? So the number of vectors that you're going to have in your standard basis for Rn would be, you have 1 over here for 1 in the second position, 1 in the first position. You're going to have 1 for 1 in the second position, for third position, for fourth position, and then up till the nth position, right? So you're going to have n vectors here in your standard basis for Rn, right? And you denote it as E1 to En, right? So E1 is this guy over here with 1 in the first position, and En is 1 in the nth position, which is the last position here, right? Okay, so E1 to En is your standard basis for Rn, right? And you have n vectors over here. So that tells you that the dimension for your vector space Rn is in fact n over here, right? Okay, and this is a general formula, and we saw this for the case of R2 when the dimension of R2 when this n is equal to 2 is equal to 2. And the dimension of R3, when you're looking at three-dimensional vectors, the dimension of R3 is 3, right? Okay, so if you have R4, the dimension of R4 is going to be 4, right? Alright, so if we have polynomials of degree at most 2, right? So remember, polynomials of degree at most 2 would look like this right-hand side here, right? The degree is at most 2 over here, right? So you could at most have a term in x squared, right? Okay, so what would be the dimension of your vector space of polynomials of degree at most 2, right? Well, we showed previously that 1x and x squared would form a basis for this vector space of polynomials of degree at most 2. So what that tells you is that your basis is, well, the basis is 1x and x squared, so the dimension of this P2 over here, polynomials of degree at most 2, right? The dimension is 1, 2, 3, right? Because you have 3 elements in this basis here, right? Okay, and more general. Okay, so one thing you want to note is if I have polynomials of degree at most 2, right? The dimension isn't 2. The dimension is in fact 3, right? So 2 plus 1, right? Okay, so let's consider the more general case, right? So I have vector space of polynomials of degree at most n, right? Okay, so what does that look like? That actually looks like this over here, right? Your polynomials would be a0, a1x, and the highest order term would be x to the n over here, right? With some coefficient a to the n, right? All right, so a basis for that, for this vector space of polynomials would be 1, x, x squared, x cubed, and so on, right? Because, okay, you'd want the 1 to pick up constant terms, you'd want the x to pick up this terms in x, and so on, right? So your basis for polynomials of degree at most n is 1x, x squared, x to the n, right? And you want to notice that, well, the amount of these, right, is actually n plus 1, right? Because you count from x, starting x to the 1, x to the 2, and you're going up. So we're going to have up from x1 to x to the n, right? And then you have 1 more over here. So it'll be n plus 1, which is n plus 1, right? Okay, so your vector space of polynomials, this would be a basis, 1x, x squared up to x to the n. You have n plus 1 of these, right? So that tells you that the dimension of this vector space of polynomials is n plus 1, right? Okay, so let's recall R3, right? So what is R3? R3 is a set of the vector space of three-dimensional vectors over here, vectors with 3 components, and it's all possible vectors like this, right? So you're free to choose whatever A, B, and C that you want, right? Okay, and a basis, the standard basis for R3 is what you get by putting 1 in your first position and 0 everywhere else. Likewise, for your second vector, you put 1 in the second position and 0 everywhere else. And then for the third vector, for your standard basis vector, right, 1 in the third position and 0 everywhere else, right? Okay, so notice how you're getting this standard basis for R3, right? Basically, for each position, you just replacing the position there by 1, and you're making everything else 0, right? And in fact, you did that for R2, right? Because when you're doing it for R2, right, this is what your vectors in R2 would look like. And to get the standard basis for R2, right, where you have your first component there, you have 1 and everything else is 0. That gives you your first basis vector. And then for your second basis vector, you put 1 in the second position and 0 everywhere else, right? Okay, so let's now consider your vector space of 2 by 2 matrices, right? Okay, so your vector space of 2 by 2 matrices, if you want to notice, it's a 2 by 2 matrix with 4 entries in it. And as a set, right, it's just you're free to choose whatever scalars you want over here, right, for the A's, right? And your vector space of 2 by 2 matrices, I mean, the vector addition is standard matrix addition, and the scalar multiplication is multiplication of a matrix by a scalar, right? Okay, right. Now, if you're looking over here, right, you notice that you have 4 positions, right, where arbitrary scalars could go, right? So if you're going to form a standard basis for your 2 by 2 matrices, you follow a similar idea to what you did, say, for R3, right? For your first position, you put 1 and then you put everything else as 0, right? For your second position, let's call the A1 to your second position. You put a 1 there and then 0 everywhere else, right? For this position here, you put a 1 there and 0 everywhere else. And then for your bottom right hand corner, you put a 1 there and 0 everywhere else, right? Okay, and this here, this would form a basis for you for your 2 by 2 matrices here, right? It takes, and you should check, right, that these 4 matrices here, or vectors, if you're regarding them as elements of a vector space, right, these are linearly independent, and that they in fact span is this vector space of matrices, right? Anyway, so your basis of 2 by 2 matrices consists of these 4 vectors here, right? And therefore the dimension of the vector space of 2 by 2 matrices is 4, right? Okay, so well, how many positions do you have over here, right? The amount of positions that you have to put in this 1, right, and 0 everywhere else, it's 4, right? And that comes from the size of the matrix because you have 2 rows and 2 columns, right? And more generally, if you had m rows, right, and you had n columns, right, then the amount of positions that you would have would be m times n, right? Okay, which means that if you form in your basis in this fashion over here, right, for each of the positions, in the case of m by n matrices, for each of the positions you'd have a 1 and then 0 everywhere else, right? And then you have m times n positions like that, which means that for your m by n case, you're going to have m by n matrices that are going to look like this. And that tells you that your basis for m by n is going to have m times n vectors in it, right? So the dimension of matrices of size of the vector space of matrices of size m by n, right? The dimension of it is m times n, right? And you want to notice that this formula here works for the 2 by 2 case, right? Because in the 2 by 2 case, the dimension according to this formula would be 2 times 2, which is 4, right? And we have 4 over here for this basis for 2 by 2 matrices. Okay, so let's consider this 3-dimensional vector space R3 here, right? We saw already that E1, E2, and E3, right, is standard basis vectors where E1 is just 1, 0, 0, the E2 is 0, 1, 0, and the E3 is 0, 0, 1, right? This would form a basis for R3, right? Okay, so this is what I have in this table here, right? Okay, what I have in this table is that I have R3 and I have E1, E2, and E3. Right, these three vectors, standard basis vectors, would form um, a basis for R3. So the dimension of R3 is the number of vectors in this basis, which is 3, right? Okay, so now let's consider the xy plane, which is this gray plane here, right? So in this case, well, what would be a basis for this xy plane, right? A basis for the xy plane would just be these two vectors, 1, 0, 0, and 0, 1, 0, right? Okay, so these two vectors here would form a basis for the xy plane here, right? Okay, so the xy plane here, a basis is E1 and E2, where E1 is the first vector, E2 is the second vector. So the dimension of the xy plane is the amount of vectors in this basis, which is 2, right? Alright, okay, so now let's say just consider your x-axis here, right, which is this red axis here, right? Okay, so what would be a basis for this x-axis over here, right? Well, a basis for this x-axis would in fact just be this 1, 0, 0 here, right? So the E1 would be a basis for this red axis, which is denoted over here, right? Okay, so this E1 over here is a basis for your x-axis, right? Okay, so notice what happened, right? We had three vectors that were for the entire three-dimensional, what were three vectors, E1, E2, and E3 formed a basis for the three-dimensional space, right? Then I had two vectors that would form a basis for my xy plane. Okay, so I needed one less for the xy plane because, well, the xy plane isn't the entire, is a strict subspace of R3, right? Okay, and then when I form my x-axis, when I look at my x-axis alone, right, then the x-axis again is a strict subspace of the xy plane. It's not the entire xy plane, it's only a part of the xy plane, right? And the basis of that just contains one vector, right? Okay, so notice when the subspaces got smaller, right? So I had R3, right, which is the entire thing. And then to get the xy, which was smaller than the R3, the amount of basis vectors was one less, right? And then for the line, right, which is again a subspace of xy plane, right, which is smaller, right? I took out one more vector, right? So this has now the basis for it just has one vector in it, right? Okay, and I can actually keep going like that, right? Because we mentioned that your trivial subspace, which is just a zero vector by itself, right? Okay, so this point over here, the origin over here, that in fact is a vector space. It's your trivial vector space, right? Okay, so what would be a basis in this case for this, right? Well, to be consistent, right, each time it got smaller, right, and I'm doing this in a sort of systematic fashion, right? Okay, each time it got smaller, you lose elements of your basis, right? So over here, right, I had three elements in my basis: the xy plane, which was strictly contained inside the R3, right? I set it up over here so that I could take out one element in my basis and get a basis of the xy plane, right? Okay, so I can keep taking out elements of my basis, right? So once I get to my x-axis, which is one-dimensional, right? What would be a basis for just the origin itself, right? So a basis for the origin itself you'd get by removing this basis vector. Right now, if you remove this basis vector over here, you'd end up with a set with nothing in it, right? And the size of that set is in fact 0, right? And notice everything is consistent over here, right? You have three-dimensional space that you started off with. And then you have your xy plane, which was two-dimensional, which had two basis vectors in it, right? Your basis has two vectors in it, right? Then you have your x-axis here, which is one-dimensional and had one vector in it, right? When you came down to the origin, you don't need any basis vectors to describe it. So your basis for your trivial subspace is empty, right? And the size of the empty set is the amount of elements in your empty set is 0, right? Okay, so the dimension of your trivial subspace is in fact, well, to be precise, the basis for your trivial subspace is the empty set, and the dimension is the number of elements in that basis, which is in this case 0, right? Okay, so that is how we're gonna define the dimension of and the basis for your trivial vector space, right? Okay, so this is what this is saying over here, right? If I have an empty set, right? The empty set by definition is linearly independent, and the span of the empty set is the trivial subspace, right? In other words, just the dot at the origin, right? Okay, so because the empty set is linearly independent and it spans this trivial subspace, when you take the span of it, you get this trivial vector space, right? Then what that means is that your empty set is a basis for the trivial vector space, right? So your empty set is a basis for this vector space that consists of this origin over here, right? And the empty set has no elements in it, right? The dimension of your so the dimension of the basis of your trivial vector space, okay, so the basis of the trivial vector space is the empty set, right? And so the dimension of your trivial vector space is the number of elements in a basis for that trivial vector space. And the basis for the trivial vector space is the empty set. So the number of elements in that basis, which is the number of elements in the empty set, is 0, right? And that's the dimension of your trivial vector space. Right, so let's take a look at something called Goldilock's principle, right? This is Goldilocks and the three bears and so on, right? Okay, so what this is doing for us is that if I have a vector space and I know what the dimension of it is, if it's small n, right? If I have subsets of a certain size, right? If it's bigger than, if the subset is bigger than, of size bigger than the small n, or if it's size smaller than this small n, right? Then I can actually say certain things about that subset, right? I can tell whether it's, to some extent, if it's linearly dependent or if it spans and so on, right? Okay, so let's look at an example of this, right? This might be the easiest way to see it, right? So I have some vector space that's going to contain my subset, right? So the example that I'm going to use over here for my vector space is R2, right? Okay, and R2 we know by now is two-dimensional, right? Okay, so the dimension, which is denoted by small n over here, is 2, right? Okay, so your first statement in this Goldilocks is that if I'm looking at if I have a subset of my vector space, right, and that subset has size bigger than the dimension, then the subset is automatically linearly dependent, right? Okay, so for example, right, I have this subset over here, right, with 3 elements in it, right, 3 vectors in it, right? Okay, so right, well, you could go do it the hard way and use a definition of linear independence to check to see if this is a dependent subset or not, right? Or, I mean, you could realize that this 1, 1 you can get as by adding these two, right? So these vectors are dependent, right? But what the Goldilocks is saying for you is because this is of size 3, right? And that 3 is in fact bigger than the dimension 2, right? Then this set is automatically linearly dependent, right? So it's actually a nice way to check to see if something is dependent, right? The first thing you could do is you could check the size, right? And if the size exceeds the dimension of the space, the vector space in which the vectors live in, right? Then you know that it's linearly dependent, right? Okay, so this is You want to be careful about using this, right? Because it is possible that you could have, say, two vectors, right? If one vector was a multiple of the next one, right? Then that would be of size 2, right? And that doesn't mean that if it's of size 2, it's going to be independent, right? It's only if the size is bigger than the dimension, then you know it's linearly dependent, right? And it's still a useful piece of information, right? Okay, so let's consider now that I have a subset of my vector space, and now the size of the subset is less than the dimension, right? So the example that I'm using over here is that the vector space is of dimension 2, right? And this subset now is of uh, size 1, right? Okay, and this is a subset of R2, right? Okay, so what Goldilocks is saying over here in the second case, right, is that if the size of your subset is less than the dimension, then your subset does not span the vector space, right? Okay, so this subset over here, if you took the span of it, you would not get the entire vector space R2, right? Matter of fact, what you get is you get the x-axis, right? Okay, so if you have a vector space of a certain dimension and you're looking at a subset and the size of the subset is less than the dimension, then this subset cannot span R2, right? Okay, and this is nice because it saves you a certain amount of work in, right? If the subset falls into this particular case, right, you could just invoke this Goldilocks, right? Right. Okay. Now, the third case is that if I do have a subset of the same of the size that is equal to the dimension, right? So remember, the small n is the dimension, which in this example, the dimension small n is equal to 2. And I have a subset of size 2 now, right? Okay, and if I happen to know that this subset is linearly dependent, right, then it automatically spans, right? Okay, and because it would automatically span, it would mean that it's a basis for R2, right? Okay, now why is that sort of useful? That's useful if I want to find a basis for R2, right? And I come up with a subset like this over here that has size equal to the dimension, which is 2, right? And I just show that it is linearly independent, right? Then the spans comes for free, right? And I don't need to show the spans, right? The spans is just automatic given these two conditions, right? And therefore I will get linear independence and spans, and so the S would be a basis, right? Okay, and then your fourth case is similar, right? What you have again is a subset that of size equal to the dimension, right? And I know if I happen to know that it spans beforehand, right? Then I no longer need to check the linear independence because the linear independence will come for free, right? Okay, so if the size of the subset is equal to the dimension and I know that it spans the vector space, then it is automatically linearly independent, right? And therefore it's a basis, right? So it's similar to tree, except now what there's only one thing that you need to check is the spans, right? Over here, what you do is you check the linear independence and the spans comes for free. Over here you check the spans and then the linear independence comes for free.